I'll get started today. Again, my name's Dan Ufner. I work for USDA, NRCS, that's the Natural Resources Conservation Service, out of a soil survey office here in Olympia, Washington. My job is essentially to conduct updates and maintenance on soil survey information, some of which I'll be presenting today. So this soils talk will be kind of in three sections. Soil formation, we'll talk briefly about formation and what makes some of Washington's soils so unique and the diversity that we have in our soils here in Washington. Then I'll talk about soil survey in general, kind of give you a little bit better understanding of what soil survey is, how it's produced, and hopefully that information will allow you to better use the available data that you can find on various platforms such as Web Soil Survey. So, and that is what's called SURGO data. So that stands for Soil Survey Geography Data. So that's both the spatial data, the polygons, the maps, and then the tabular data, all of the soil interpretation and soil property data that's behind those maps. So that's kind of the three stages of the talk we'll hopefully go through today. So first, when we talk about soils and soil formation, it's important to think about, well, what is soil? What are we trying to define? What are we trying to discuss when we're talking about soils? And it kind of depends on who's asking the question. Are you a geologist, an engineer, a farmer, an ecologist? All have kind of their own definitions or thoughts about what soil is. But as a soil scientist and as a mapper, as somebody out there trying to identify soils, we kind of think of soils as an ecological perspective or approach, where we're looking at soils as natural bodies with their own unique morphology, their own unique characteristics on the landscape, and of the soil forming factors, which we'll discuss here in a second, that help create and define those soils. If you think about soils in that way, you can start to think about how soils change based on those different factors, and it helps explain some of the inherent and dynamic soil properties. So then that will help you in your use and management of soils, whether you are a geologist, whether you're an engineer, whether you're a farmer, to better understand the soils that you have on the landscape. So why do we care about soils? Soils perform several important functions for us and for the ecology of systems. So we talk about soils as sustaining plant and animal life, all the way up to providing support for the structures that we live in. Acts as a buffer, filtering out chemicals that interact with the soil across the landscape. And a big part of soils that we look at is the regulation and partitioning of water on the landscape. So when we talk about soils and how they form, we look at what's called the 5 soil forming factors. And the interplay and the interaction of these factors across the landscape help create the soils that we see. And so those factors are climate, organisms of biota, parent material, topography or relief, and time. And the way you can kind of look at this cycle is climate and organisms acting on parent material of a certain relief over time. And we have some really unique and diverse climatic conditions as well as parent materials here in this state that have helped create some of the really diverse soils from east to west as you move across this state. So we'll talk a little bit in brief about some of these soil forming factors and the functions that they play. So climate and organisms the first two, we have really diverse climate in the state. So we go from those photos on the left, the landscape and soil photos on the left of the screen, in an area where you might have precipitation in the single digits, all the way up to west side soils over on the western slopes of the Olympics and the rainforest areas of the Olympic Peninsula, where you can have over 250 inches of rainfall. And so that difference in rain really impacts the weathering rates of the soils that we see. And so increased weathering, the increased filtration into the soil of water and acids and different organic acids and clays, and movement within those soils from that varying amounts of rain and water on the landscape will help actually break up and deepening those weathering profiles of the soil. So, you know, the soils on that left-hand side of the screen are relatively shallow. Those white plates that you see, that's actually calcium carbonate that's deposited right near the surface, because there's very little rainfall, so there's very little water leaching that calcium carbonate from the system, so it actually accumulates right near the surface and actually can create impermeable layers, if essentially cemented plates in place, restricting root growth, restricting what water does move through that system. Whereas the soils of the west side, we have a lot more rainfall. We have that which results into the buildup of vegetation, so we have a larger amount of organic matter at the soil surface. And so that rainfall interacting with our organic matter, actually we have lower pH water moving through that soil. So it takes all that calcium carbonate out of the system. So we really don't have that buildup of calcium carbonate in the soils over here on the west side. So that's just one kind of difference that you can see from that interaction of climate and organisms based on where you are in the state. Parent material, that's another huge amount of diversity that we have in this state as far as the parent materials that the soils form in, so that climate and organisms act on to create soils. So we can have soils forming in residual or residuum, which is basically soils forming in the parent materials that were laid down in place. So that would be those soils forming across bedrock. So that picture in the upper left, that's basalt columns. So those soils are forming in place on that bedrock. We have glacial materials, which is a huge parent material across, especially across the northern half of the state, all through Puget Sound, and here in Olympia, where I'm actually giving the talk today. We have another kind of glacial sediment, which is loess. So this is material that was brought down with the Missoula floods and then had blown back across the Palouse area and deposited huge, thick areas of loess, really silty sediments. So those loess hills that you see around the Pullman area and the Palouse, again, that's actually a glacial material. And then we have volcanic eruptions are a huge source of parent materials here in this state, with volcanic ash admixture on a lot of our soils, where we've got some soils forming really in just varying deposits of ash, especially around, we did a project around Mount Rainier just recently, and with several of the soil series that were set up were the dominant parent material is ash. And so the parent material in parts is going to impart specific characteristics to the soil, especially those inherent characteristics like soil texture, coarse fragments, or gravel, cobble, stones, some chemical properties such as cation exchange capacity. Those different parent materials are going to impart some of those characteristics on the soil, as well as how fast those soils develop. So a soil developing in bedrock is going to take much longer to develop than a soil that's forming in, say, those loess areas, which, you know, it's basically non-bedrock. The soil's already broken up. And so you can get soil formation creating faster in those cases. Topography. So are you in an area of the site where it's collecting water, or are you in an area that's running, where water is running off of it? Topography is going to impact whether you're going to have collection of organic matter, collection of clays, collection of erosive materials coming downhill, or are you in a spot where that material is leaving it from? The other point that topography could play and interact with climate and organisms is aspect. So you could have two slopes with the same slope percentage, but one is on a north-facing slope and one is on a south-facing slope, and they could create different soil types based on the climatic conditions and as the result of the aspect. And I'll show an example of that in a little bit. And then the last piece is time. How long have those soils been in place, and how long has those other four factors been in place and interacting with one another to form particular soil? So you could have two soils with exactly the same climatic conditions, topography, biota, and parent materials, but you could have one soil, like here on the left, this inceptisoil, that might be 10,000 years old, and the soil on the right might be 100,000 years old. And so again, the time in place is going to be another big factor. And we have soils, you can think about the soils here in Washington, you could have soils that are brand new, so alluvial soils that are constantly changing by bringing in new flood materials. Landslides, you know, landslide goes through, that kind of resets the time frame to zero in that soil profile. And then you could think, move on the scale, we've got these glacial soils forming glacial sediments, glacial tills, glacial outwash sediments, glacial lakebed sediments, and those are in the range of 10 to 15,000 years old. So here where we're sitting in Olympia, the soils here are 10 to 15,000 years old on those glacial sediments, but in the south part of the county, south beyond the edge of those glaciers, you can get into soils that are 50, 100,000 years plus old. They've been in place that long. So how these soil forming factors interact with one another is through soil forming processes. So we have additions, losses, transformations, and translocations. And visually this shows kind of what those processes are. So you can think of an addition as things like precipitation, so a climatic factor, or buildup of organic matter, so a biotic factor, but that buildup is an addition to the soil. Then you can have things like transformations. So a transformation would be the breakdown of organic matter. It could be the creation of secondary minerals into clays. So the breakdown of the parent material and the transformation of that material into silica clays. The other big example I like to use is the formation of mottles or redoxamorphic features. So those splotches of red iron rust stains that you see in the soil that indicate the height of a water table. So that would be a transformation. You have iron in the soil being transformed by the microbes who are using it in the place of oxygen in the presence of saturated soil conditions. And when that iron changes phase, when the soil is saturated, it becomes mobile. So that's one transformation. And then when it hits an area of oxygenation, it transforms again because it becomes oxidized, and that's that red splotch that you see. So that would be a transformation. The transfer would be that movement of that iron in the soil. That would be a transfer or translocation. A loss would be that the leaching of that material completely away from that profile. So that earlier we talked about the calcium carbonate being lost completely from the soils here on the west side because it's leached with the the more acidic groundwater, that's a loss. A loss could also be something like the removal of organic matter or the mechanical removal of material from the surface of the soil, or a landslide. That could be a loss. So here's an example of kind of all of that, what we just talked about, the soil forming factors and soil forming processes together. So the picture on the left is the kind of broad scale view of this mountainside slope. And then the two soils on the right are the two soils that form in those two areas that they're pointing to. So we've got this really dark, thick, dark, organic rich soil with not very much horizonation at all in that top right picture that's pointing to the area of the meadow or the range area of that side slope. And then the bottom right photo is a forested soil where you can see that really gray, ashy colored material near the surface, overlain by organic soil deposits. And then underneath that gray zone is that really bright red soil horizons. And so these differences are really created by the soil forming factors and processes that are in place in these two locations. So we can say that the parent material is probably the same here on this side slope. We could say the topography is the same as far as maybe perhaps slope, but maybe the aspect is different. And that aspect difference has created differences in the climatic and organic factors impacting those two soil types. So on the area of that meadow area is probably a south or west facing slope, and so the snowpack that might build up there is going to leave fairly quickly in the spring and summertime, and it's going to heat up faster in those months, and so it's not able to support the growth of trees in that area. As in contrast, you've got the area in the woods that might be a north or east facing slope, and so it's going to stay cooler longer. So that snowpack that's going to build up is going to actually stay longer, and the trees help insulate that snow, and so it's going to stay on the soil surface a lot longer in those areas. And so what ends up happening, along with the vegetation differences, you get that buildup of organic material, those really acidic needles from the conifer species that are growing there, and then you get that snowpack on top of that organic horizon, and because that snow is going to melt a lot slower, it's slowly leaching into the soil, trickling water through that organic. It's picking up acids as it's flowing through that. And when it hits the soil, the mineral soil, it actually that acid starts to leach out any organic matter, clays, aluminum, and iron from that first mineral horizon, and it's leaching through that layer and then being deposited in layers below it. And so that gray zone is what we would call an E horizon, where those organic materials, irons, aluminums, are actually exiting the system. That's the E. And then it basically deposits below that horizon, and that's why you get that really dark orange, sometimes you'll see black and orange mixed together right below those E horizons. And this is a really common process in the Cascade, especially in the Cascades here in Washington. So these are kind of two types of soils, and so that snowpack with the water leaching through, that's going to be an addition of water to the system. That loss of aluminum and organic material and clays from that E layer is going to be a loss from that horizon, and it's also a transformation of that material because it's becoming more mobile. It transforms again in that next horizon below it, and that's why we get that color pattern that we see. So that's that kind of interaction of of the soil forming factors and processes together. So you can see, if you have an understanding of these factors and processes, it really helps explain the types of soils you're going to see out there, and it can also help explain potential limitations of the soils in that area, whether they're inherent limitations that are going to be very difficult to get through use and management to get past, or if they're dynamic properties such as organic matter content or cation exchange capacity or pH. Some of those things can actually be amended and dealt with through use and management. So that tremendous diversity of the forming factors that we have here in Washington has helped create some of the really diverse soils here. It's a really cool place to work if you're a soil scientist. We have 49 soil survey areas across Washington State. So the map actually shows what soil surveys are actually completed here. So the green are all published and available. The yellow are initial projects, so those are projects that are ongoing. And then the gray are actually those areas that have not been mapped and are currently non-projects. And typically those are the federal lands, and I'll explain that in a minute. But you can see Mount Baker, Snoqualmie, Gifford, Pinchot, and Hannaford are the three big areas that are currently not mapped. So those are our soil survey areas. We have over 9,500 map units. We have greater than 25,000 components in this state, and I'll talk about what those are. And we have 1,700 individual soil series here in this state, representing 11 soil orders. So to give that you perspective, there are 12 soil orders in our taxonomy, and we have 11 recognized orders here in this state. So in comparison, you know, states like Nebraska or Georgia have 7 soil orders mapped in their states. And Nebraska, which is larger in size than the state of Washington, only has 411 soil series maps. So they have a quarter of the soil series that we have here in the state. So that kind of ends our soil formation piece of the talk. We'll now switch to soil survey, kind of give you an understanding of soil survey and what we do. And I'll give you kind of a broad perspective at first, and let me go back to this previous slide. So you can see a lot of the soil survey areas actually match up with our county boundaries here in the state. And that's really how soil surveys were done up until very recently. Most of the surveys were done county by county, so each county had their own specific soil survey area. And that can create problems, especially if you have counties completed by different soil scientists at different time periods. And so you could actually get differences in data right at a county line. And, you know, we talked about soils being in this, you know, kind of an ecological perspective. They really shouldn't change based on a county line. They should change based on those combinations of forming factors we talked about. So the way we do work today is more on an ecological approach. So these are what's called MLRAs, or major land resource areas. And so these are going to be areas that have been split up, these broad groupings, based on broad physiographic, you know, landform, climate, land use, resource concern type boundaries. And so we're sitting in MLRA 2, which is the Willamette and Puget Sound valleys. And, you know, our office, the way these soil survey offices are set up now are by MLRAs. So each of our offices have responsibilities for specific MLRAs, and all of our projects are based on this MLRA approach. So in a sense, the soils within MLRA 2, the major soils in MLRA 2, really shouldn't be found in the adjacent MLRAs of 3 and 1. And so this allows us to create projects and update the data based on this ecological approach where we get seamless data across county lines within similar these similar soil forming factor related aspects. So this is the MLRA concept. We have this actually nests within what's called land resource regions, and so we have 3 land resource regions in the state. Then it goes to MLRA. Below that is another unit called Land Resource Unit, or Conservation Resource Area, and that's kind of more like a general soil map unit, so that kind of scale. And then below that would be our actual soil map unit. So that's kind of the nested system and the approach we look at today in setting up our soil survey projects. So NRCS is in charge of creating an inventory of U.S. soil resources across all private lands of the U.S. And all private lands includes all state lands. All federal land is dealt with in a different approach, and so we at NRCS would actually have to get MOUs with our sister agencies to actually map federal lands, and that's probably why some of those areas of the state, Mount Baker and Gifford-Pinchot, haven't been mapped yet. But we do have an MOU with like Olympic National Park, and that's why that project's actually getting mapped as we speak. So a lot of folks ask me, well, why are you working on the data? Why are you still mapping soils? Everything has already been mapped in these counties. Well, the other part of our mandate is to keep soil survey relevant to changing needs and to provide up-to-date and relevant interpretations of and in a useful form. So that useful form would be things like web soil survey, which we'll talk about in a minute. And then the other part is to promote soil survey and provide technical assistance with things like I'm doing today. So before we dive into soil survey, some general concepts, I'd like to give a few caveats to our data. So soil survey information can be used for general planning purposes, but oftentimes you need on-site investigations, especially if you're looking at a scale-dependent project. So if you're putting in a septic system, or if you're putting in a foundation, you want to have somebody come out and actually look and do work on the site for that site-specific information. But the soil survey allows all of us to communicate together about the soils that we observe on the site, and allows that transfer of information. And especially, it allows in the planning process you to focus in on areas where you would want to have your specific site-dependent work to take place. So again, scale dependent. Most of our mapping, most of our SURGO, that soil survey geographic information, most of our data is a scale of 1 to 24,000. So that's 1 inch on the map equals 2,000 feet on the ground. So the width of our line is 20 feet. And so the minimum size delineation is going to be 5 to 6 acres in size. And so you can really understand, if you're looking at a very site-specific management practice, that you're going to need to have some on-site information to back up the soil survey, especially if you're looking at something that's less than that 5 to 6 acres in size. So soil survey in the field, a lot of our field tools haven't changed hardly at all since the beginning of the soil survey program, which is over 100 years now. So we're still digging holes by hand out there with shovels. We're still, getting together, looking at road cuts. And so some of that work has really not changed. But what has changed is how we describe the soils, the data we collect while we're out there in the field, and then how we create the maps that we use. And with GIS and technology that have come in place in the last 15 to 20 years, it's really changed how we do our mapping as an agency. When I started my career, I was actually working using a lot of the similar techniques as those photos on the left-hand side of the screen with stereoscopes and aerial imagery, aerial photographs, and you're actually drawing your lines on the hard copy photographs. Today, you know, and in that time, you might have a geology map, you might have a topography map, you might have some different layers, but they're all spread out on your desk in front of you, and you're trying to create this mental model, you know, just looking at the various layers, but you can't look at them all together at the same time. And with GIS, that's something we are now able to do. So in our new mapping, we're actually able to create a much better product, especially in areas where we have things like LiDAR that give a really detailed image of the ground surface, so we can actually pick up landforms much better than we used to be able to with just stereoscopes. So that's another reason we're conducting update work in some areas, is to really get that line work a lot better and a lot closer to what those landforms look like out on the ground. Soil survey is a snapshot in time. It's a snapshot of both the management and use when that soil survey was created, of the technology that was available when that survey was created, but also of the landforms that were in place at that time. So if you can see in this photograph, this is just west of Oakville, that water body, the river flowing from south to north in the photo is the Chehalis River. And so that 134 map unit, that polygon that says 134 right in the middle of the water with that gravel bar, that's a soil map unit. The 169 polygon now actually flows through what is now land. So that just shows you how much that river has moved since that original data was mapped. The original mapping was done back in the 60s and 70s in this part of Grays Harbor County. And so we are actually doing an update project right now to update this data, both the tabular data but also the spatial data, because we actually have LiDAR for this whole valley now. And so we're going to be able to get fix these issues in the survey. So again, survey is a snapshot in time, and so knowing that, it will help inform some of the maps that you're looking at. If it's not accurate, it's probably because that mapping was done in the previous years. So I'd like to skip this and then we'll go back to that in a second. So let's dive in and talk about soil map units, soil components, soil series. So if you look at this diagram, the majority of this cross-section represents a single map unit, that 1224 Chehalis-Maytown. And all of these soils that are shown on this cross-section, the Chehalis, the Maytown, the Rennie, those represent single components within that map unit. So a component is essentially a soil type, a representative soil type that we find within a map unit. And a map unit generally is going to be areas of the landscape, landforms that we pick out that have similar topography, climate, parent materials, again, those similar soil forming factors, and we would split those areas out because they would potentially have differences in use and management. And we pick out those representative landform areas that show a particular pattern, so we're able to pick them out across the landscape consistently. So that would represent a map unit. The soils that we find within that map unit, the representative soils within that map unit, are what's called components. And they have a specific range of characteristics, and they're found in the specific areas within those map units. And we'll talk about different types of map units in a second. So let me go back. So some soil components are what's called soil series. And the series is basically the highest level of our soil taxonomy. Remember, we said we had 12 soil orders. in the state, or in soil taxonomy. And then it's a hierarchical system. So it goes from order, suborder, subgroup, great group, family, and series. So series is the highest level. And so that's that name, Bellingham. So when you look at a soil survey map unit or a component and it says Bellingham silty clay loam 0 to 3% slopes, that Bellingham is a soil series. And each level of this hierarchy tells us something about that particular soil. So this Bellingham soil is an inceptisol. It's a weakly developed soil. It's an aquep, meaning it has a high water table, it has reducing conditions, saturated conditions, really close to the surface. The endo tells me that the water table is coming from below up. It's rising water table, so it's not a perch system. The vertic is telling me that it's got shrink swell clays. And then the family tells me even more specifics about the particle size class. So it's going to be have clay content greater than 35%. That's that fine. The mixed is the mineralogy. The superactive has to do with cation exchange capacity. The non-acid means it has a certain acidity range, and the mesic has to do with the soil temperature range. So that tells me, a soil scientist, each step along the way tells me something specifically about that soil. And so when we talk about soils and soil series, that's why we use the series concept, because it's another communication tool. We can tell something's a Bellingham versus something that's an Alderwood. They have these specific differences and ranges of characteristics. So again, soil series is a type of soil component, and those are the dominant components we map. Another component that you've probably seen is what's called a miscellaneous area or a miscellaneous land type. These are essentially non-soils, so things like river wash or pits, rock outcrop, urban land. You've probably seen some map units with those in the title. Those are miscellaneous areas. So those are, again, specific components. So on this cross-section, these chehalis are well-drained soils, so they're going to be found on the kind of convex portions of that landform in the map unit. The Maytown is a moderately well-drained soil, so it has water table within 3 feet of the soil surface during the winter months, so it's kind of on those concave, linear, flat areas that are going to collect water. And then, so that's those are the two dominant soils, and then we have a minor inclusion of Rennie, which is a poorly drained soil. So those are going to be those concave areas that are going to collect water, and that water is going to stay around for a long period of time. And so that would be a poorly drained Rennie soil. So that shows you kind of what the component concept and the map unit concept together. So when we're setting up map units and setting up components, this is something to keep in mind, and it's very difficult to keep in mind even as a soil scientist. So when we're out there, we're trying to find the representative condition. So the representative components within that map unit. The other piece we're looking at is similar soils. So we could have two soils within that map unit, and they might vary maybe 5, 10%, 20% in gravel content. One might be very deep, and the other one might be deep, but they don't really have any impact. The difference between them have minimal impact on use and management. So we would go with the more representative soil and call that other soil a similar soil, and it would not be named in the map unit, and it would not be listed in our component list. And then the other piece we're looking at is limiting. So we're trying to find those components that are actually limiting to a broad base of use and management. And the big things we look at are depth to an impermeable layer, depth to a water table, or soils with drastically different textural makeup. So that would impact available water capacity and other important soil properties. So those are things to keep in mind. So as far as soil map units go, I'll talk about the first two. So we have 4 different types of map units. First is what's called a consociation, And I like to use this as a visual depiction. So this is Neapolitan ice cream. So we've got strawberry, chocolate, and vanilla. So you can think of consociation as a single component dominated map unit. So each flavor represents a consociation. So that chocolate would be one map unit dominated by a single component. The other soil map unit you folks have probably seen is what's called a complex. A complex is two or more dissimilar components, so one is limiting compared to the other, that occur in a regular repeating pattern, but they're mapped so intertwined on the landscape we can't pick them out as separate map units at the scale we're mapping. And so this would be, you could think of mint chocolate cookie ice cream. So the chocolate cookie is intertwined with that mint ice cream, and so that would be a complex. And you always know it's a complex because it actually says complex in the map unit name. So that Copeland-Mitchell Bay complex. And the first name is always the more dominant component within the map unit. So that's going to have the more dominant amount within the map unit. Association is similar to a complex, except we could map them out separately at the scale that we're mapping, but for whatever reason, use and management, they're just mapped as an association. And again, it says association in the map unit. This is pretty, it's more consistent in areas like BLM land where it's one or two use and management across huge areas, and so they mapped associations. And then we have what's called undifferentiated groups, where you have two or more components, but they're not always together in the same map unit polygon. So a complex, if we call something a complex, those two or more components are always within the polygon. Undifferentiated group means that you can have one or the other located there. And then soil map unit phases are, you can think of a phase as whipped cream or walnuts or chocolate chips on top of that ice cream flavor. So it's going to be other specific characteristics that are within that range for that particular map unit. So they could be surface texture phases, so like Chehalis silt loam versus a Chehalis silty clay loam. So those are two map units with different surface texture phases. Could be slope phases, and that's probably what most people are familiar with. So you've got alderwood, gravelly, sandy loam, but they're on various slope breaks, 0 to 3, 8 to 15, 15 to 30% slopes. And we've broken them out on those slope phases because they have impact on use and management. And then we have things like depositional phases. So we're right in the middle of the Cowlitz County survey when Mount St. Helens blew. And so they had to go back and actually remap several areas, and they added that overblown phase on top of the map units they had already set up. So if you can start to think about soils like we did in that cross-section in three-dimensional space as compared to two-dimensional space, it really helps your understanding of soils on the landscape and how they relate to one another. So how does water move through one soil map unit to the other, for example? So that kind of ends our general soil survey discussion. I'd like to talk a little bit about soil survey that's available in Web Soil Survey, so the actual SURGO data. Again, Web Soil Survey and SURGO is our official data, so it replaces all of those old hard copy manuscripts that you were used to using. If you go to our Web Soil Survey page, the main page, that kind of center column in the middle of that right photograph, that will give you a quick, if you're just interested in getting a soil map, that'll give you a quick rundown of how to create one. And then if you look at the links on the right-hand side of that screen, they look something like this. So if you're interested in better understanding and better using Web Soil Survey, I would really recommend going through the getting started with Web Soil Survey and then how to use Web Soil Survey. It'll really help you get the most out of the platform. So just really briefly, if you're unfamiliar with using Web Soil Survey, the first thing you need to do is create an area of interest. And I won't really go through this, but there's a whole series of ways of actually creating your area of interest. So when you open up Web Soil Survey, you're actually opening up data for the entire nation. And so that's why you have to create an area of interest, because it'll clip that data just to the area that you're interested in. So you can type in your address, you can do state and county, you can do section, township, and range, and so forth. And every iteration of Web Soil Survey that comes out, we're actually in a brand new version of 3.2. They've increased the ways to create your area of interest, and recently they've actually you can actually use shape files and bring them in and cut the data. So here's your soil map, and what's nice about this is those on the left-hand side of the screen is the map unit names and legends, and if you click on one of those hot links, the soil map unit name, you can get a brief map unit description, which is great because it outlines the properties and qualities of that map unit and the geographic setting. So you get an understanding of, as well as the components that are found within that map unit. And then not just the soil map unit, but with Soil Data Explorer, in the old soil survey, you can only look at our interpretation data in a tabular form in tables. With Web Soil Survey, you're actually able to create visual depictions of specific soil properties and interpretations. And so, for instance, in this map, we're actually showing rating of hydric soil map units. So those units that have hydric components or wetland soils that form in wetland conditions. I go back just one slide. So another nice feature is this search feature. So when you have your area of interest created, you'll have a search option that's available to you in Web Soil Survey. So if you're interested in forestry specific interpretations like site index, you can actually type in forestry, you can type in site index, you can type in trees, and what will happen is you'll get a whole list of interpretations, properties, maps with links that will link you directly to those specific interpretations of properties. So it's a nice way of finding the data because it can be overwhelming. So again, here's like forest productivity, tree site index. You can actually have some aggregation methodology to create the map. And your aggregation method kind of will depend upon the type of map unit you have. So if all the map units you have are consociations, you might go with dominant component as your aggregation method because that consociation is made up dominantly of one soil type, one component. But if you have something like a complex, you might want to run something like weighted average because that complex is made up of more than one dominant soil type. So maybe you want to have an average condition across that map unit. So you could get site index that's a weighted average, for example. And then you would get a depiction like this. The other piece that you can get is the soil reports themselves. And so the soil reports will again give you the soil tabular data in a table format, and so you can get a lot more information sometimes in a report than just a visual depiction. So I only have 5 minutes left here, so I want to go through something new that's been developed. Nicole Jacobson here at DNR has worked with our regional technical office in Portland, a soil scientist named Steve Campbell, and he has actually come up with some forestry interpretation ratings. I know here at DNR you have your own soils layer with some specific interpretation data that we did not have in Web Soil Survey. And so Steve has actually recreated some of these interpretations, a compaction, a displacement, and a puddling potential. What's nice about this is we can store this criteria, and then the criteria that he used can be used on all existing data any new data and any update data that we do on the Surgo. And while he could not get it completed in time for our yearly refresh, we refresh all of our data, all the Surgo data every October. So these interps aren't available yet. They will be available next year. But he does have a geodatabase that's available, and I know Nicole has it. So if folks are interested, I'm sure we can work out a way to get it to you and help you decipher the ratings. But just as an example, so this is the new compaction potential rating using the Surgo data. So this is all of our existing data. And so the compaction high, medium, low, so those soils that are have a high potential for compaction versus those soils that have a low compaction potential. And he has a complete write-up on how he developed these interpretations and what the ratings mean. So this is the Surgo data. So again, it's quick and it's tied to our G-Surgo product. So you can get these really quick maps that statewide maps. So if you compare that to, this is something that I created based on the DNR mapping, and I created a same interpretation, the compaction potential, using the DNR interpretations, high, medium, low. Again, you don't have as much coverage across the state, but if you look at the statewide distribution of the potential rating, so here's the DNR, and here's the new data from Surgo. From the areas that are overlapping, the data is fairly consistent. So I think Steve did a really good job of creating this new interpretation. So again, those are available upon request. So that should be it for today. Here's a website for you to get access to Web Soil Survey and some of our other products.